Hello and welcome back. Contour integration today. We're going to be looking today at the integral from the real integral from 0 to infinity, log of x over 1 plus x to the 4 dx. And the answer that we ought to be getting, I did remember this time to actually look it up before I'm going to start this lecture. So it's going to be minus pi squared root 2 over 16. Okay, as per usual, we're going to consider with contour integration the integral of a log of z 1 plus z to the 4 dz over a suitable contour. And it's worth noting, first of all, let's work out some residues. And the residues, first of all, of this particular function, if we solve the equation z to the 4 is equal to minus 1, the principal value will be e to the I pi over 4, so we're going to have e to the 3 pi over 4, e to the 5 pi over 4, every 90 degrees basically, 7 pi over 4i. Okay, next is to consider the integrand. Look at this log of z. So we're going to have a branch point at the origin, and consequently a branch cut. A branch point, if we have, for example, the square root of z, we're going to have a branch point at z is equal to 0. If we have the log of z branch point at z is equal to 0, if we had the cube root of z plus I, we're going to have a branch point at z is equal to minus I, and so on. So let me just draw the contour that we're going to be using. And the contour that we're going to be using is going to be a semicircular contour. Now this is where the 0 to infinity will come from, but now we're going to have a little problem. Okay, let's put real and imaginary in z. The problem with a branch point, so we're going to go through it, and therefore we must indent, so we can take the origin out with a little semicircle as per usual for radius epsilon. And where we have the branch point now, we're going to take a branch cut somewhere. Normally we would take the branch cut probably along the coordinate axis, but here it's actually easier to take it in an arbitrary direction, something like that. So it doesn't interfere with what we're going to do up here at all. So first of all, let's trace our curve in an anti-clockwise direction. So it goes like this. Let me label, this is a different color pen. This is our gamma. And from the poles, the simple poles, only 2 of them will be inside a big gamma. One is at e to the I pi over 4, and another one at e to only those 2 at 3 pi over 4. This will be there, and therefore we don't really care about those 2. And for simplicity as well, let's do a little bit more labeling. Minus r and minus epsilon. And let's label as well what colors that we use. It's got a purple pen. I cannot see it anymore. Somebody stole it. I'll have to use the brown pen, I guess. This is our gamma 1, this semicircular arc here. And this small semicircular arc, let's call it gamma 2. Okay. I just want to say something, pardon me, for this particular integral. We could actually use, in fact, if you're experimenting with this, and the first time I tried this particular integral, I tried the keyhole contour, something like this. I took the branch cut like this, and then what happened when I went above and below, so trying to obtain my real integral from these straight line sections, they in fact cancelled out, so it doesn't quite work for this particular integral, the keyhole. So that's the next, that's my next try basically, to actually see what can I do instead. Okay, so next thing now in all of this is to compute some residues. So let's do, first of all, the residue at e to the I pi over 4. So I'm going to do the work here and I'm going to wrap it off once I obtain the actual numbers. You got to excuse me, I got a runny nose all of a sudden as soon as I started the lecture, and at the same time a bad cough has come just to annoy me. Z e to the I pi over 4 log of z over 1 plus z to the 4. This is 0 over 0, so I'm not going to factorize this. I could, it's probably quicker to use L'Hopital's. So that is the limit as z tends to e to the I pi over 4. Differentiate top and bottom. So bottom, first of all, is going to be 4z cubed, product rule here. So we got 1 times the log of z plus this bracket untouched times the differential of the log of z, which is 1 over z. And so far, when we're taking the limit, when we're putting that in there, that will all gone, and therefore we're going to get the log of e to the I pi over 4 over 4 e to the 3 pi over 4 I. It's going to be I pi over 4 on the numerator over the 4, that's this bit here, e to the minus 3 pi over 4. And what do we get from there? From there, what we're going to obtain is, oops, I missed the I there. I'm going to get I pi over 16. I'm going to switch this into sines and cosines. So that's going to be the cos of 3 pi over 4 minus I sine 3 pi over 4, which will give me I pi over 16 cos of 135 is negative root 2 over 2. Sine of 135 is positive root 2 over 2, but I go a minus, so it's going to be minus root 2 over 2. And if I tidy this up a little bit, we're going to get an I pi over 32 and also put the root 2 there, and that will give me now a minus 1 minus I. And if we hide the I inside this, we're going to get I times I, which is a positive 1 with a minus in there. So pi root 2 over 32, 1 minus I. I hope I haven't made any silly errors with this particular residue. So let's leave that here. And now, rather than rewriting all of this, it might be a good idea to just change the I pi over 4 for 3. So I do apologize, be lazy. 3 pi over 4, we can just squeeze it in there. 3. I do apologize, I'm going to try to blow my nose. This is all the after COVID effects. This is one of the videos that I'm recording straight after my discharge from hospital. So you got to excuse me for this. Sorry. Okay, thank you. So 3 pi over 4 as well here. And now when we're taking limits, this of course will cancel when I put e to the I 3 pi over 4 into this term here. So it will leave me now the log of 3 pi over 4. And when I cube this term, it's going to be 9 pi over 4. And from here, let's rewrite this. I'll have to remember not to wrap this off because it's the residue of the previous pole. So let's be careful and leave that in there. So this is equal to I 3 pi over 4. And here I've got 4. This is the quarter from there. E to the minus 9 pi over 4i. And if we write this, it's going to be I 3 pi over 16. And now this, if we 9 pi over 4, if we add 2 pi to that, it's going to be minus pi over 4. So it's going to be the cos of pi over 4 is still going to be a minus. So it's going to be minus I sine of pi over 4. And this is going to produce, okay, let's have a look at this. 3 pi I over 16. Cos of 45 is root 2 over 2. Sine of 45 is exactly the same, but we have a minus root 2 over 2i. Let's put that in a box that's from before. So this is equal to, factorize out a 3 root 2 over 32. Still an I on the outside, and we go 1 minus I. And let's get rid of this I, but timesing it inside, so it's going to give us 3 root 2 over 32. I times I, we got now a positive 1 minus I. Is that right? Minus 9 pi over 4. Don't like the look of that. So let's double check my workings here very, very quickly. 3 pi over 4. We've got, we're adding 2 pi, so it's going to leave us minus pi over 4, cos of negative pi over 4 minus, I made a mistake in here actually, so that should be a plus, because there's already a, wait a second, no, I put that on the outside, so still a minus, so that is that bit in there. And then when we times it all out, we're going to have 3 root 2. I times I is a positive 1. So that's this bit here. And then we go plus I. What am I doing? I'm just stupid. I don't know why I put the minus in there. It's, okay, that's correct now. So that's the 2 residues. So before I move to the next line, because I'm going to use the residue theorem very, very shortly, it might be a good idea to actually add these 2 residues together. So I have a final answer and ready. So these are still some rough workings. Pi over 2 over 32, 1 minus I, plus 3 root 2 over 32, 1 plus I there. And if we factorize a pi root 2 over 32, it's going to give us 1 minus I plus 3 plus 3i, which is pi root 2 over 32, 4 plus 2i, which will simplify further to pi root 2 over 32. Oh, no, not over 32. I'm going to multiply it, factorize the 2 rather outside. 2 plus I. So that is the sum of the 2 residues. Okay, let's make some space on the board. So this is the important number now that we need to make sure we keep intact. So there we go. So now by the residue theorem, so essentially what we're going to do is we're going to integrate section by section around big gamma, and we should get, of course, by the residue theorem, 2 pi I times the sum of the residues inside gamma, which is this quantity here. So I'm going to put a curly bracket. Doesn't matter where we start, so we're going to go around gamma 1 first, plus minus r to minus epsilon, and then we got the arc around gamma 2, and then from epsilon to r. Close curly bracket, f of z, where my f of z is of course the log of z over 1 plus z to the 4, dz is equal to 2 pi I times this quantity here, actually let me just not put the bracket, times pi root 2 over 16 2 plus I. Quite disgusting, this particular expression. Okay, so now quite clearly our integral is going to come from the straight line segments and we have to show some kind of estimation that the contribution around gamma 1 first of all and then around gamma 2 is in fact is equal to 0 in the limiting cases as r tends to infinity here and as epsilon goes to 0 for this particular one. Okay, so let's start with the approximation or rather estimation around gamma 1. So the integral around gamma 1 of f of z dz. We're going to parameterize it, of course, around the gamma 1. Z is r is e to the I theta, circle radius r dz is ir e to the I theta d theta, and theta runs from 0 to pi. Okay, so for this particular one, therefore, 0 to pi, and now we need to put everything in parameterized form. So we got log of r e to the I theta, that's my log of z on the numerator, 1 plus z to the 4, so that's r to the 4 e to the 4 I theta, and the dz, I'm going to write it on the numerator here, ir e to the I theta, and let's put the d theta outside the integral, so no, outside the integrand rather, so we're right at the end, d theta. Okay, before I take these brackets, actually I'm going to do it at the same time. I'm going to move the modulus inside the integral, so that's going to be less or equal, and it's going to look like that. But I'm going to also use the rules and break this particular quantity to the log of r plus the log of e to the I theta, I r e to the I theta. I'm just merely copying the rest of the quantities now. Mr. Theta there, for e to the I theta. Okay. So now I'm going to take modulus of the top and modulus of the bottom separately. So we're going to have equal 0 to pi, the log of r, the log of e to the I theta is just simply I theta. So that is in fact inside a modulus. So that's this bit here. Actually, I'm gonna do it in steps the first time, and we have another approximation. I'll speed it up on the second one. So this is basically this quantity here, I r e to the I theta, modded on the top, and then modded at the bottom, e to the 4 I theta d theta. I'm showing quite a lot of detail for people that actually need it and need to follow where bits are coming from. Okay, after that, now we are using the rules of the modulus for real or complex. So wherever we have multiplicative quantities, we can actually write it as individual moduli. So the mod of that times the mod of I times the mod of r times the mod of e to the I theta. We cannot do that on the denominator because of the plus. 1 plus r to the 4 e to the 4 I theta d theta, which is equal to, okay, e to the I theta modded is equal to 1. E to the I, anything real here, is equal to 1. Just switch into causes and sines and take modulus is always 1. Well-known fact, that's a 1. And the modulus of I is, of course, 1. the modulus of R is just R is a positive quantity. So we're gonna be left on the next line with R modulus of log of R plus I theta over 1 plus R to the 4 e to the 4 I theta d theta. And now we're going to use, of course, the triangle inequality for the top. Log of z plus w is less or equal to the mod of z plus the mod of w, where the z is the log of r and w is the I theta, or the other way around, doesn't really matter. So this will be applied on the top, and on the bottom we have another member of this family which says w plus z modded is greater or equal to the mod of z minus the mod of w, and that is greater or equal to 0. In fact, I want it to be greater or equal to 0 because I want distinct values for my w and z. And you must say, how would you know that z and w, the mod of z is bigger than the mod of w? Well, if it isn't, I'm going to just swap them around. So when I get the inequality when these two moduli produce a positive quantity. And the reason I want to do this is because I want to flip it. So 1 over z plus w now, it will reverse the inequality to 1 over the mod of z minus the mod of w. And I'm going to use this inequality on the 1 over, in fact I forgot to put moduli there, I do apologize when I took moduli on the top, so it should be moduli there. I do apologize for this. So this is my very last line. I'm going to have to rub off to make some space. This lecture is not one of my best. I do apologize, I'm not very well at the moment, so I'm missing things, and I hope my brain is working still, because for the last month or so I haven't done anything. Okay, so now we're going to have an R, and this, by the triangle inequality on the top, is going to be less or equals, which I put at the top, the mod of the log of R, which is like that, but of course that's a positive quantity, particularly as R tends to infinity, as we're going to do it. So it's R is bigger than 1, basically. I mean, if you think about it, with the position of the pole, which is distance 1, so the R is bigger than 1, so it's another justification why I don't actually need moduli from that, plus the modulus of I theta in this particular quantity. And at the bottom, it doesn't really matter which one is your, we can treat that as the z and this one as the w, is going to be, in this particular case, 1 minus mod r to the 4 e to the 4 I theta d theta. Okay, let's make some room. I'm going to go right to the top and continue with this estimation. I'm going to have to go a lot faster for the estimation around gamma 2 because there's fairly repetitive steps, and at the moment I'm showing way too much detail perhaps, so otherwise the lecture is going to get absolutely massive in length. So from this particular line, what do we have in here? We have, first of all, this is going to be less or equal because we had lots of less or equal along the way. And that was pi there, 0 to pi. And we have r log r mod of I theta is, of course, mod of I mod of theta, which is just theta. So plus r theta for this particular quantity. And on the denominator we have 1 minus, now we can take moduli individually, so it's going to be r to the 4 and e to the 4 I theta. As before, e to the I real is, because we got I and then we got 4 theta, which is a real quantity, that's 1. So that is, can be thrown away. And the mod of r to the 4 is, of course, Actually, we don't need that, equal now. And it's just r to the 4. And we can actually write this as, I'm going to factorize an r, 1 minus r to the 4 on the outside. Pull out the r from there, and the r to the 4 from there. Remember, the modular has gone now. I'm going to throw it away. And what we got inside is 0 to pi 1 plus theta d theta. And of course, in the, oops, no, that's not correct. We got a log of r there, r log r plus theta. And now we can do the integration with respect to theta. That's going to be, of course, r 1 minus r to the 4. And integrating with respect to theta from 0 to pi is going to give us, of course, pi log r, oh, for crying out loud, pi log r, back to my old self, silly things, plus a half theta squared. So it's going to be plus a half pi squared. So that's the integration of theta with respect to theta, and then evaluate it from 0 to pi. So what do we get in there? We're getting something which is of the order, actually let's not put orders, we're going to write first of all pi r log of r over 1 minus r to the 4 plus pi squared r over 2 1 minus r to the 4, which is of the order log r. This r will cancel. This is just ignorable compared to the r to the 4. Is of the order log r on the top, and this r will cancel me to r cubed. And this one is going to be of the order, this we can throw away, of 1 over r cubed, which of course, as r tends to infinity, dominant terms are here really, and this will tend, both of them will tend to 0 as r tends to infinity. Okay, so we have found so far that the contribution in the limiting case as r tends to infinity around gamma 1 is gone. We're going to do the same thing now, the same estimation around gamma 2. And as I said, I really need to speed up the workings. Otherwise it's becoming a little bit tedious, a little bit repetitive, but it's the same ideas. Okay, so the estimation is around gamma 2, f of z dz modded. Now that's going to be around gamma 2, epsilon e to the I theta, I epsilon I theta d theta. And now, because we're going in a clockwise direction, not that it really matters, is from pi to 0. So let's put our bits in. So it's going to be pi to 0, f of z, log of z. So it's going to be the log of epsilon e to the I theta. And on the denominator, we're going to have 1 plus z to the 4 plus epsilon to the 4 e to the 4I theta. And let's put on the numerator, of course, the dz, which is I epsilon e to the I theta d theta. Okay. And still modulus there. So we're going to do quite a few things at once now. So we're going to move the moduli inside, so that creates less or equal. And this pi to 0, you know, because it's still inside the modulus, if I flip this limit, it will generate a minus, but because it's still modded, I can throw it away. So I'm going to actually, just for looks really, change to 0 to pi. It doesn't really matter. And I'm going to mod the whole thing, and then I'm going to mod individually all the bits. And at the same time, I'm going to split this log. So I'm doing a lot of things. So log epsilon plus log e to the I theta modded times the mod of I times the mod of epsilon times the mod of e to the I theta, and Now we have mod 1 plus epsilon to the 4 e to the 4 I theta close mod and the d theta there. So I've done a few things. E to the I theta modded is 1, I is 1. So we're going to have now a little bit of a tidy 0 to pi. Epsilon does not need a mod now anymore, right at the front. And then we got the log of epsilon plus I theta inside the mod over 1 plus epsilon to the 4 e to the 4 I theta close mod on the denominator d theta. I'm going to use the triangle inequality on the top and this kind of inequality that says 1 over on the bottom, as I did on the previous approximation. So both are in fact less or equal. So less or equal 0 to pi, and now I'm having epsilon, and then is that plus that on separate mods. And if I say is less or equal to the mod of log of e, so you can, if you want, put it on inside the mod, because as epsilon goes to 0, this will go massively negative really. And we're gonna have the mod of I theta, which is this theta. Perhaps I multiplied it out actually. And on the denominator, 1 minus, or the mod of 1 minus the mod of this, and then of course I'm going to write it, but I'm going to throw it away in a second. So minus the mod of this, but then when you mod it individually, this is, of course, it has modulus 1. So in fact, and we don't really need any moduli there. So it's going to be minus e to the 4 d theta. So that is now, so far so good. So that is equal to, let's factorize out of this like we did in the previous example. Epsilon 1 minus epsilon to the 4, 0 to pi, log epsilon plus theta, d theta, integrate that, 1 plus epsilon to the 4, and that's going to go theta times that, and the theta will become pi minus 0, which is pi, log epsilon, and that's going to be a half theta squared, so it's going to be a half pi squared. And if we look at what's going to happen in there, I'm going to say this is equal. I'm going to write it a little bit different this time. This is of the order epsilon, because of course the dominant term as epsilon goes to 0, okay, the dominant term this time is the 1, so that's going to be order epsilon times pi log epsilon plus a half pi squared. And without much to write, as epsilon goes to 0, this quantity here, this is finite, half pi squared, it'll be dead, so this bit here will definitely go to 0, and epsilon log epsilon, it's a result which of course we ought to know. This quantity goes to 0 as epsilon goes to 0, as epsilon goes to 0 faster than log e goes to negative infinity. It can be proven using L'Hopital's rule, so at the moment I'm not going to dwell upon it. So that definitely goes to 0 as epsilon goes to 0. So we've done it hopefully a lot quicker now. We made some time. So the contribution around gamma 2, we've proven that in fact is 0 in the limiting case, which of course is as epsilon is shrunk to nothing. Okay, so now we need to make some room. So let's clear some of this. We don't need all of this. And let's look at what's happening here. This board is very, very messy. Needs a good clean, I think. That's what it is. So I do apologize. I hope it's nice and clear on the video. I'm going to clean it straight after this one. Okay. So what I can say here is I can say the integral, actually let me just write it here, from minus infinity to 0. I'm going to write as f of z at the moment, dz, plus the integral from 0 to infinity, f of z dz, is equal to this quantity here. So we simplify this a little bit. Perhaps we should. What do we get from this one? We're going to get a pi squared over 8. That's the 8 from that. We're going to have a root 2, and we're going to have a 9. We start getting things which look like that. Okay. And then we have a 2 plus I, and perhaps we ought to write this as, that's a minus 1, that's the I times I, plus 2I. So perhaps we should write it as minus 1 plus 2I. Okay, so we're going to be a bit tidy on this. Of course, if I flip the limits here and generate a minus, and the integrals cancel if we go into x's, so that's not actually quite true, because of course we got logs there, we got branch points and branch cuts, and strange things happen now. So first of all, where shall I write this? Maybe I should just write it on the top and then afterwards carry it at the bottom. If you look at this particular segment, that's the 0 to infinity. So that's epsilon went to 0 and now goes to infinity. So if we look on the right, z is x e to the 0I, which of course is x. The dz is dx e to the 0I, which of course is the same as dx. What else we need to work out? The log of z, just in case. And the log of z is of course the log of x e to the 0I. We're going to write it in its full glory so we are happy with what we're doing. That's the log of x plus the log of e to the 0I, which is the log of x plus 0I, which of course is the log of x. So what this means is, on this particular integral, when we parameterize it back into x, this is exactly the same, but just swapping from z into x. Not to infinity, log of x over 1 plus x to the 4 dx, and that of course is equal to pi squared root 2 over 8 minus 1 plus 2i. Okay, what about the other one now? Let's make some room and let's see what happens if we go to the integral on the left. In other words, along that section. So what happens in there? So that is on the left. There, the z is x e to the pi I, which of course is minus x. Okay. The dz is dx e to the pi I, so that means that's another minus 1 minus dx. Okay, what about the log? The log of z is the log of x e to the pi I, which of course is the log of x plus the log of e to the pi I, and this of course will give us the log of x plus pi I, or I pi, shall I say. And let's think about what happens in here. First of all, x is, the z will be replaced by minus x, which means the limits will swap signs. So first of all, that's going to be from infinity to 0. but we have also another minus from the minus dx. So that means we're going to have infinity on the top and 0 at the bottom. And now we're going to have in there the log of x over plus I pi. Remember, that's your log of z, and 1 plus, does the x make any difference? The x, of course, careful, the log of z doesn't go to the log of minus x. We have actually put it correctly, x e to the I pi, and this is correct. There's no minus x in here, okay? However, the bottom, the x to the 4, okay, we need to put this x instead, but because to the 4 is, of course, x to the 4, and the dx, of course, the minus, we use it to swap the limits. So what happens now is a bit of a final tidy. So what happens? We have 0 to infinity, and we're having two lots of log x and log x over 1 plus x to the 4 dx plus an I pi not to infinity 1 over 1 plus x to the 4 dx. That's from this bit here. Let's split the right hand side to imaginary and real. Minus pi squared root 2 over 8 plus pi squared, we've got pi squared, the 2 we're going to cancel that into a 4. We still got the root 2, and then we got the I. So if we look now at what happens, we're trying to find our integral, which we got two lots, that's the real part. And of course, our integral here is indeed, I'm going to write it here, the log of x over 1 plus x to the 4 dx not to infinity is in fact equal to the half, which is minus pi squared root 2 over 16. Well done me, because I managed to survive it and not make any silly mistakes. And of course, we're getting this one as a bonus, not the standard way of doing this. It's just that I think I've done this one in the standard way, I guess. In fact, if we look at the imaginary part of this residue, what does that give us? It gives us not to infinity. This is like a little bonus, but not that we needed it. It's just total waste really for that. The i's cancel, so we're going to have now a pi. Cancel the pi with the pi squared, pi root 2 over 4, I think. Okay, so, and I think that's also correct. Okay, that's enough for today. I hope my voice, because I have to say this is the first lecture, actually not the second lecture post-COVID, and my breathing is not quite there, and I don't know if I sound loud enough, and you can follow the video. If not, my apologies. It will improve with time again, and I hope you find it useful. And for the time being, I'm going to be signing out. Okay.